Okay, so we could use this one if you want to find it. All right. All right, so guys, we're gonna start our next talk with Michael Albergo. His talk is going to be about matter transport perspectives on sampling, generative modeling, and beyond. So Michael is a postdoc at Corinth, a student of mathematics science. His research interests lie at the intersection of generative modeling, statistical physics, with a focus on designing machine learning models to advanced scientific computing. He received a PhD under the supervision of Cal Grammer, Jan LeCun, and Eric van den Jende at NYU. His field is at the University of Cambridge, and he received his AB at Harvard University. From August 2024, he will be a junior fellow at the Harvard Society of Fellows and IFA fellow at MIT. Welcome, Michael.
Okay, thank you, Wanki, and thanks to the rest of the organizers for inviting me. Give me 1 second, I'm trying to figure out how to get into video off of my slides. Okay, great. Yeah, so today, as Wanki said, I'm going to talk about some measure transport perspectives on problem sampling.
Okay, the visual login, we need to plug the HDMI. Yes,
It's good. Yeah, okay, super. So I do that.
Full screen. So this one is small. For some reason, it's that we use with. Oh no, it's fine. It's fine. Got it. Okay.
But nevertheless, you would like this full screen of that. Okay, right. So yeah, I'm going to talk about some measure transport perspectives on sampling and generative modeling, with emphasis on problems in science. Full disclosure, I don't work on graphs at all, but I am interested in problems that are related to geometric deep learning. I know there's a big intersection there. So what I'm going to talk about today is sort of a suite of tools that we are interested in applying to highly geometrically structured problems from a generative modeling perspective. Okay. So before I go any further, I want to move this bar, and it would be great if it just disappeared for me. But there seems to be no freedom to do that. Click more.
Yeah, there's time loading.
Here. Okay, before I go any further, I just want to quickly thank all my collaborators and vendors who contributed to this work in various ways. So this talk is really going to be about the bottom half of collaborators here. And our aims over the next year or two are to really apply this to what's going on with the top half of collaborators. Okay. So I'll start with a trope. Okay, that really the social and natural worlds that we inhabit are complete with a complex structure. Okay, and it's often beneficial to interpret this complex structure probabilistically. I know we've seen great strides in that in our social world. For example, if we want to try to understand the underpinnings of human communication and language, or for example, the aspects of human creativity and visual understanding related to problems in video generation. We can look at abundance of data and construct algorithms now that give us sort of an ensemble of possible interpretations of our designs. So if I ask, for example, for a flower growing on a windowsill, we have these text and video models now that are just kind of remarkable and make me think we're playing with fire a little bit. That could give you a perfect rendition of that in a matter of moments. And then on the other side, our natural world is also sort of replete with this probabilistic structure. We can ask about problems in simulating the structure and conformations of quantum field theories, of the conformations of molecules, or perhaps the ensemble of future predictions of dynamical systems. And here, often we don't really have much data, but we do have theory that we'd like to use to try to inform how we think about solving these types of problems under a probabilistic interpretation. Okay. And so that's just to frame sort of a standpoint of where we're at. My research interests that are motivating me to ask this is that I'm interested in computational problems in statistical physics. Okay, this could be things in high energy physics, advanced matter, in chemistry. And I'm particularly interested in designing machine learning techniques that are inspired by those underlying physical problems. Okay, and that sort of meet the demands of scientific computing, have sort of control over the correctness or bias in the types of models that we're using. So this might involve designing generative models on manifolds, for example, circle, or products of these circles to try to simulate aspects of the strong force in holding together the inside of a proton. And I'm going to take some motivation today from the ascendancy of generative modeling over the past 12 years. Okay, so in 2012, our best depictions of being able to represent underlying data distributions sort of was stuck at NIST. We were able to generate handwritten digits using things like Boltzmann machines, and progressively over the past 10 to 12 years, the power of these models has grown extremely rapidly. Now we can query a diffusion model in 2022 and say, draw me an image of two bears doing chemistry in the form of a cartoon, and you can get that in a matter of seconds. So this sort of is the problem setup I want to think about, right? This is sort of a probabilistic generative modeling paradigm. And I'm going to state what our goals are in thinking about this. Okay. We're going to want to estimate an unknown probability density function that I'm going to call ρ1. Okay. And we're going to either want to do this through sample data or access to, for example, an unnormalized log likelihood function, like an energy function in physics that tells us about the likelihood of the configuration of the molecule or the arrangements of spins on a lattice, things like this that we might be interested in. But today I'm really going to just focus on the first part because of time constraints. And what I want to focus on is the fact that through this ascendancy, right, what has emerged is sort of what I'll call a metric transport perspective on the success of these models. Okay, building maps between probability density. So I'm going to ask, and sort of be a guiding question for this talk, is how can measure transport help us understand these successes, and then eventually build more performant tools that we can also interpret. So that's going to be the agenda. I'm going to put this whole part 2 as ask me offline because I'm not taking up the time of other people here. But what I want to talk about is really new algorithms for dynamical measure transport. Okay, building maps between these different probability densities that we want to study. So I'm going to frame what that problem challenges, and I'm going to talk about a method that we've been building out called stochastic interpolance to try to address this, and then I'll go through a few applications about what you might want to do with this. Okay, so just to lay out what the transport framework is. Okay, this is the picture we're going to be working with. I'm interested in trying to understand this density ρ1, right? And I'm going to do that by introducing a new density, a very simple one perhaps, that I'll call a base density ρ0. Might be something like a Gaussian. And my aims are going to be to build some sort of reversible map that I call T here that says for every sample I draw from ρ0, I put it through T and it pushes it to a sample under ρ1. Okay, so you would say T pushes the density ρ0 on ρ1. Okay, and this is actually a means of expressly defining the likelihood of ρ1, defining the type of density. Saying if we know the density ρ0 and we know aspects of this map T, namely its Jacobian, and have an ability to compute the determinant of that Jacobian, then we actually have a definition for what the density ρ1 is, and this is a way of defining basically the density we study. But there's an obvious problem here is that if I had this map a priori, my problem would be totally solved. We don't know what it is, and we need to devise algorithms, methods, and perspectives to try to infer what this map T is from data or from descriptions of this problem. Okay, so if we only have a parametric model of this map T that I'm going to call T hat, to make it really useful, I need to balance two qualities, right? If I want to have a probabilistic interpretation of this, I need this determinant that I have to compute to be computationally tractable so that I can define the density ρ1. But also, I want to learn this T in an expressive parametric class of functions, right? So I need this T to be sort of maximally unconstrained in some sense also. So there's a trade-off here that I'm trying to really want to balance, right? We're trying to form optimization functions. And then you may have various applications in mind, right? That go beyond, for example, what I'll call some naive generative modeling, where we want to say take a Gaussian and push it forward some data distribution. You may have other interests such as domain adaptation, things like translation, or you may have, infilling of proteins, problems like this. You may have a very specific type of measure transport problem where you have a graph, a point mass that says maybe here's the weather right now, predicted for me an ensemble of future potential weather outcomes that come at a later time, right? And so we want to have a flexible language that can deal with all these types of different problems. So that's what I want to focus on, is how do we harness measure transport for these various tasks? Okay, and then how do we actually learn these maps once we lay out these perspectives? Brief history on it, just to give some context that people have been thinking about this for a while. So, it may be hard to learn this map T in one go. You might want to break it into smaller maps that allow for it to be more computationally tractable. And this is sort of the original perspective on this problem that goes back to Chen and Gopinath in 2000 in the paper called Gaussianization, which tries to sequentially learn to connect the data they have to such Gaussian distribution. And then Eric Van den Einde and Eston Tibach and his postdoc sort of extended this idea. And the way they sort of phrased it is was a sort of perfect setup for the neural network folks to come along and say, if I have these sequence of maps that are simple transformations, maybe each of them can be parameterized by a neural network. We can put a neural network somewhere, and then the methods we have also work better. So this is the idea of Laurent Din and Danilo Rezende and George Papamakarios, where they made these TK structured invertible. Okay. But you can imagine taking this sort of k equals infinity limit here and saying, I have this map T that takes a sample x0 from row 0 and pushes it into a sample x1 from row 1. And imagine that it actually emerges from continuous time flow. Okay, and this is the perspective of Ricky Chen, who I don't see him here, but I know he's talking a bit later, and Will Grathwohl in the paper that they call Fjord, that adopted what we know as a neural elite, sort of said, let's put parametric optimization problems in theme with differential equations and see what comes out of it. And when you do this determinant that we had to deal with before now becomes the trace of the instantaneous change of what I'm going to call a velocity field. Okay, and that velocity field B, which I'm stressing because it's going to be the object of study for the rest of this talk, is really now that's the sort of central thing we want to focus on. Okay? The trace of its instantaneous change can actually be estimated now instead of having directly computed determinant, and this is sort of a favorable property. So because we're going to think about this velocity B, right, as the thing that solves our probability flow, okay, it's going to provide our transport between densities. Worth introducing all the notation we have for that, and then I promise there'll be some interesting results. So the thing we want to endow with this velocity field B is what I'm going to call a flow map, which is capital X, little t here. Okay, and this flow map is such that if I take a sample X from row 0, which is in this case would be a simple unimodal Gaussian, and I put it through this flow map, which emerges as the solution of this ODE, okay, then the evolution of X under row 0 will follow one of these flow lines. Okay, so xt of X, right, is going to be some sample from the intermediate density row T. Okay, and if I go all the way to t equals 1, then if this is all learned perfectly, if I know what the B is that does this, then this is going to end up exactly as a sample under row 1. Okay, so it's a way for me to endow this map, right? And we say the flow map all the way to time t equals 1 is the transformation that I want. Okay, so if I can solve this ordinary differential equation, which you can do, for example, with the Euler integrator, and something like this, then you have learned your new flow. Okay. So if we do this, we can also ask what's happening at the level of the distribution. Okay, if I define a row 0 here and a row 1 here, and I'm saying I imagine what the flow map would do for all the samples under this density, then there's a row t, a time-dependent density, that you can define anywhere in between these two densities. Okay, for this one is this Gaussian, this one's this mixture of three Gaussians. Okay, and what we would say is that if this is solved, right, if we actually go from row 0 to row 1 with a velocity to B that does this, then rho t satisfies what we call a transport or continuity equation. Okay, and so what we're going to want ultimately is to find the B that solves this problem for us. Okay, and so we'll assume that these sets of densities are smooth and that this is a well-posed problem, And our aims are going to be, what is the sufficient PTX, the function of time and position, right? That allows us to endow this probability. Okay, what would be the simplest paradigm that we could imagine doing here, right? The dream scenario would be just to figure out a way to perform regression on the true velocity field that connects these guys, right? But it's kind of a chicken egg problem, because if I knew what the true velocity field was that fulfilled my flow map, my problem would be over, because I would already have the solution. So that's problem number one. And the second problem is, if I were to try to perform this regression to learn this V everywhere between these two densities to build this flow, then I need to be able to sample the time-dependent density, this rho t, at any time slice in between here, right? That allows me to learn it everywhere in the interval that I care about, which I define as between 0 and 1, but you know. So how can we work exactly on this interval? Choose an arbitrary rho 0, an arbitrary rho 1, and somehow learn this velocity field under this regression defect problem. Okay, that's what I want to lay out. To do that, we're going to introduce this thing that we call an interpolant function. Okay. So an interpolant function is going to be some function that I call x. Okay, it's a function of time, samples from the initial density x0, and samples from the target density x1. Okay, and it can be any very simple function that just has the following quantities, namely qualities, namely at time t equals 0. Well, this thing should just evaluate to x0, and at time t equal 1, it should just evaluate to x1. Okay. And the purpose of this is to say that if you are randomly drawing, so let me give you a simple example. Very simple one is just 1 minus tx0 plus tx1. That's about an interpolant function that you can use. But the purpose of this is saying, if I'm randomly drawing x0 and x1 from some density, some coupling, where I get an x0, I get an x1. This could be, you know, randomly drawing from each of the marginal densities. I draw something from the base density, I draw something from the target density. But it could also be more complicated. If you do that, and then you evaluate this interpolant function, then actually this sample now, xt, x0, x1, is a sample from some intermediate density rho t x, okay? So this guy is actually now a sample in the intermediate density connecting the two. So you could visualize this by drawing samples at any time slice, by drawing an x0, drawing x1, constructing the interpolant, and you get this sort of smooth transport between the Gaussian and the three densities that I was talking about. In fact, you know, we can state what this density is sort of formally, but it's not super useful to think about. It exists. This is a way of defining an intermediate density, some path in the space of measures between the two that we thought about. Okay. And what's going into this definition of rho tx? This is the guy we needed. Right? Well, one is we've chosen a way to couple we sampled x0 and x1 that we've drawn. Okay. And the other is the choice of the interpolant function. Here I chose a really trivial one. But these are the two knobs we have to decide how we're going to connect two densities and draw samples from the path along those connections. So this gives us step one of what we need to do. We're going to perform regression on the, you know, the velocity field that endows our flow map. We need to be able to sample some time-dependent density, right? So that we can, you know, over the entire interval regress what the true velocity field is. Okay, so what then, you know, we still don't know what we're regressing, right? I know how to sample this, but I'm trying to fit a model B hat to some B, but I don't know what B is. I'll just state a definition. We can discuss offline if you want about how to show that this is true, but we could say that once you have this rho tx, okay, and it satisfies the transport equation that I was talking about in the previous slide. Okay, then the VTX that does this, given the fact that you've introduced some interpolant, it's just given by the conditional expectation of the time derivative of that interpolant. Okay, so for the one that we were just looking at, where I had 1 minus tx0 plus tx1, the time derivative of that is simply x1 minus x0, and we want to take the conditional expectation of that quantity over x0. Okay. But this is still a little okay, because I can take that conditional expectation, which I just defined, plug it into my regression problem, and now I have a new object that I don't really know what it is, right? That I need to try to regress. So I haven't really helped myself too much yet. But if we just use the definition of the conditional expectation, which we were in this case integrating over this time-dependent density, row 2x. Then the definition of the conditional expectation really tells us that integrals of this quantity, just the Tower property of the conditional expectation, can actually be evaluated by just taking expectation over x0 and x1, okay, by over the base and the target densities. So if this is the case, then I can use this fact right here to write down a very simple loss function for what B is without ever having to define what B is explicitly. Okay, it's just given by the regression of our model for the velocity field B hat minus the time derivative of the interpolant taken in expectation over samples from the base and samples from the target density. Okay. So this gives us a nice simple description, right, of how to learn a map between densities by introducing a path between the densities. We've chosen a path. We chose kind of a random one, right? We just said we're going to linearly interpolate at the level of samples stochastically. And then the dynamics of that linear interpolation actually give us the way to learn B. Okay, but the real idea is that you fix a path in the space of measures, and then you can do this. Okay, so this is the same sort of algorithm that Ricky Chen might talk about a little bit later today that they've been calling flow matching. We call it the stochastic interpolant, thinking more about the object doing the interpolation. But the methods are exactly the same. And I think we all like it because it's now giving you a way to directly estimate the map that connects these densities between arbitrary densities. And, I'll get to diffusions in a moment, but, this allows us to use sort of fast ODE integrators to perform this. And there's some bounds you can write down on this loss that say that this loss controls the distance between what your model is trying to actually model, which is row 1, and what it is in terms of Washington 2 distance. But the point is, our generative model now is saying, if I have BTX, I solve this ODE, and this is basically the generative model. Okay, so that's a way to do this for deterministic mappings between, for example, this swirls density to this checker density. But you might also ask, is there a way for us to extend this picture to diffusion, what's going on in stochastic dynamics, and now the same probability density and time slice to do this over a sort of a randomized map. And I'll just quickly say that there's a simple set of criteria that fulfills this. It involves just taking the interpolant we had and appending on another Gaussian latent variable that's independent of the two margins that we care about. You take this interpolant, you say, I'm going to add a Gaussianity to it basically everywhere between 0 and 1, such that this disappears at the endpoints under some mild conditions. And then you can proceed through the exact same procedure that we had before. The velocity field associated with this interpolant is also a time derivative of the interpolant. We now have this factor of gamma TZ there. And importantly, what this allows us to do is write down the score for the time-dependent density connected. So if you want to connect this to score-based diffusion, and this is sort of the handshake that you do, it also has a very simple regression loss. So this gives us two perspectives on how to push samples from one density to another. You could do it either deterministically, following a transport equation, or you could do it stochastically, following a Fokker-Planck equation, which is basically saying, let me add on some diffusivity on one side, and then offset it with a new type of velocity field. So I'm going to differentiate between the objects you have to learn here by calling one of them B, and one of them BF or BB for forward or backward. Because the stochastic process isn't directly invertible, you need to think about the second object. And so what this is saying is basically, if I have B, then there's an ODE I solve that gives me a deterministic flow. And if I have this BF or BB, then there's a stochastic differential equation, which I can solve. This involves adding up its various steps that allows me to endow this stochastic generative model. But why bother differentiating between the two? And there's sort of a discussion we'd like to have about what's the benefit or trade-off between deterministic or stochastic generative models. And I'll just say, without having to go into too much detail, is that if you wanted to control the KL divergence between the density you're trying to actually simulate and the one your model endows, then it's actually not sufficient solely to use a deterministic mapping to control the KL divergence between. In fact, if you want to do this, you also need to control the Fisher divergence. Okay? So you can't just regress B hat and B and say I've done this to finite error and say I've controlled the KL. You also need to control this Fisher divergence. However, if your dynamics were actually pushed forward stochastically through this BN that I was talking about rather than E, okay, then you actually do get a bound on the scale divergence. So there's something intrinsically different going on here between the deterministic and the stochastic generative models. We did a little experiment just to verify that this is the case. If you imagine trying to estimate a Gaussian mixture in high dimensions, 128 Gaussian mixture model, we can solve these equations exactly there, so we can compare it to the ground truth. And we can sort of see that, just look at this plot, this is KL versus the level of noise that we're adding into the stochastic dynamics. Basically, as you approach some critical value, the KL is minimized to its greatest extent using the stochastic dynamics as compared to if you were just trying to do this with a deterministic flow. Okay. So I'm just going to pivot quick to some context for these types of methods and applications that we're trying to consider. Okay. So as a reminder, we're interested in generative modeling. Domain adaptation, we're interested in problems related to forecasting. We're going to try to exploit the fact that we can design these interpolants in a variety of ways and construct various types of couplings to fulfill these types. So just as a quick caveat to relate to these incredible score-based diffusion methods, which are an inspiration for sort of the regression problem we're trying to lay out here. If I'm sure you're familiar with this model at this point, but score-based diffusion basically says I'm going to have some data, and I'm going to introduce a noising process on that data. In fact, follows this thing called an Ornstein-Uhlenbeck process. Okay, that gives you a rate at which this sample is evolved into Gaussian noise. Okay, and what they say then is if you want to learn the reverse process to do this, you need a model for this guy right here in this SDE, which is the score function at any time t. Okay. And so score-based diffusion says the generative modeling problem is to come up with some n hat that approximates this grad log rho. But just to make the handshake here a little clearer, we can actually say this whole problem can be recasted as choosing a specific interpolant. And in fact, it's choosing one instead of putting 1 minus t and t in this interpolant function I specified, it's e to the minus t is for 1 minus e to the minus 2. And now I have an interval from 0 to infinity. But the important thing is these coefficients are fixed by the noising process that you choose in your SDE. And we're trying to open up the fact that there's a whole variety of maps that you can construct that have nothing to do with this SDE, but still allow you to endow a stochastic generative model. So let's look at an example of what are the potential benefits from trying to think a little bit more broadly. Because we have a freedom to choose any function alpha t and beta t that go into this interpolant, okay? And we may choose one, for example, that reduces the overall transport cost of pushing rho 0 to rho 1. We can ask about what are the benefits of doing this on large-scale image generation problems where diffusions are currently applied. So some of our colleagues who, in a timely manner, was the guy who authored the diffusion architecture behind this new Sora model that OpenAI put out. We're interested in investigating this, so by trying to choose these alphas and betas and trying to heighten this KL bound that I was talking about, we can sort of systematically say, let's apply that diffusion architecture that they were using, and let's do it with the interpolant and see what the benefits are. And sort of you can speed up the training by a factor of 2 or 3 and sort of push down what they measure as what they use as a measure of success is this Rechet inception distance, which compares your real images to their representations in a classifier. Okay, you can push that number way down in sort of a much more efficient manner. Compared to what you would just do with diffusion top priority. So it's kind of just a plug and play drop in for what you would do with diffusion, and it gives you a better tuning of performance. But the thing we're also trying to stress is that we're allowed to couple the x0 and the x1 in different ways now, compared to what you would do in diffusion is to sort of choose them independently. So if I'm drawing x0 and I'm drawing an x1 for some joint density, rho x0, x1, okay? You could do this independently. This could factor into a product distribution. That's what they do in diffusion. But you may know something intrinsically interesting about the two densities you want to connect. Okay, so is there a way for us to construct maps in this case? Let me give an example of what I mean. Say, for example, I was trying to draw a sample x0 and x1 from joint density here, okay? But I knew that x0 was conditional on x1. For example, I'm given I know that there exists a clean image in the world, but I'm only giving masked versions of it. They're corrupted in some way. It could be a corruption like a masking, or I want to go from low resolution to high resolution on the computer. What we could ask ourselves is, can we learn a map directly from this corrupted density to this uncorrupted density, right? Or these are GIFs, so you have to what you become. So this allows us to do this. If you wanted to do this with diffusion, you'd have to map the whole thing to Gaussian and condition the velocity field to map a Gaussian sample to your uncleaned image. And there's some hacks that have to come into doing that. So now we just want a systematic way of trying to connect these types. And again, if you do this with sort of a systematic framework, you can push down these Frechet inception distances in a much more efficient way, just by building maps between the more proximal densities rather than auxiliary maps around more complicated. But then we'd also like to consider new types of maps that are not just between these smooth densities, but potentially between point masses and future possible ensembles of outcomes that come later. So the perfect example for this is weather or dynamical systems. If I give you a measure of the weather at time t, which I call here xt, well, I'd like to be able to predict, for example, the weather at time t+1, t+2, t plus whatever, right? And we can ask ourselves, is there a simple sort of dynamical transport picture that we can write down in a learnable sense that would build the map between these densities directly, rather than doing something that's conditional on some Gaussian random variable? Okay, so this is something that you can write down. Ultimately, I'd say we want to sample from some SDE, okay, that's going to take our initial condition, which is our point mass, and push it to a whole ensemble of outcomes. How do we go about doing that? We introduce a sort of slight variant of the interpolant that we had before, okay, which now has a factor of square root t in here, okay, and we're going to couple these x0 and x1 as if they're sort of time slices. So x0 is time t, and x1 is some time t plus 1. Okay. And if these are sampling some invariant measure, for example, Navier-Stokes, something like the weather, then we can write down an associated reference dynamics. It's just about almost taking the time derivative of xt, like we've been doing this whole time with the. But we leave in this factor of square root t. And if we do this, we balance things correctly, then we can say there exists some drift, some velocity field b, okay, that is also a conditional expectation in its analytic. Conditional expectation of this type. And then this B solves an SDE that has the appealing quality that at any time t, it's sampling from the conditional density of xt given x0. Okay, so this is us saying we're going to be able to write down an SDE that takes a point mass, and in its stochastic dynamics associated with this drift B allows us to sample the entire ensemble of potential future, for example, weather outcomes, next stages in your dynamical system, etc. So what can you apply this to? Well, we took a sort of simple example of Navier-Stokes equations that has random forcing in it. Okay, so there is sort of a stochastic aspect of what happens next, but there's an invariant measure of what this vorticity field, sort of modeling this fluid flow, is going to represent. Okay, and we would love to learn the distribution of this vorticity field at the time t plus tau, given some snapshot of this time tau. Okay, and if you do this in a probabilistic sense, okay, you can actually recover. You can't see the error bars in here because it's small. What the true sort of energy cascade or structure is, frequency structure is, in the whole ensemble of predictions you should get here. If you were to do this by just trying to deterministically map omega t to omega t plus 1, there's an intrinsic bias that's going to emerge pretty quickly in this type of. Another sort of now it's hard to compete with something like OpenAI, but if you wanted to form this as a sort of video completion type paradigm, you might want to ask, given 10 frames of a video, how do I predict the rest of the video? Okay, so we want to learn the distribution of video frame coming next, given the 10 slices of video frames you have already. So this is like mapping the point mass of, I'm at this video frame, what's the ensemble of potentially causally connected video frames I'd like to learn? So you could take, for example, here's a real video and 2 final predictions of it. Of course, they're not going to exactly reproduce this real one because it's probabilistic, but they seem to naturally sort of fulfill what the potential dynamics are that you would imagine these blocks of light. Okay, so that was just to overview a method about this, new tools for dynamical transport. Okay, and what I'm really interested in is trying to apply these problems in physics, but I figured it'd be better to talk about a method rather than a physics lecture. And so, what we're trying to do is adapt this now to large-scale simulations of quantum field theory. Okay, in particular, we want to study aspects of the strong force, the force that holds protons, neutrons, and matter together. Okay, that makes up the matter class. And this is computationally an extremely large-scale task historically. Okay, so this problem was trying to understand the strong force computationally currently uses about 10% of the federal US supercomputing budget every year to run gigantic Monte Carlo simulations. And we want to rephrase that as a generative modeling paradigm. This is something we've been working on for about 4 or 5 years now, but the methods always sort of evolve as you do this. And so, we're hoping to have some good results about this in the next year or two as we scale this up to the Aurora supercomputer at Argonne National Labs. So, yeah, thanks very much. Thanks so much for this. Here's me.
Like the estimated factor.
I can't hear you, sir.
So for the factor field that we're trying to estimate.
Yeah.
Like how the model, like the network.
Yeah, and I mean, the thing is, whatever seems to work for diffusion, you can plug in here, they're both vector fields ultimately. So the UNet like that they use that maps from RD to RD is totally fine.
Also to the general, like. It's a generalized selection.
I think you could write down, you mean like the sort of neural operator that?
Yeah.
Yeah, I mean, I know people have been doing this with diffusion, and I sort of think about diffusion as just a subcase, Gaussian to data version, so I don't see why for the diffusion.
Yeah, I guess another question about the forecasting case.
Yeah.
I think one a little bit brief, but what's the reference for sensor factor? Is that like some form of Navier-Stokes equation you already?
Yeah, so in this dynamic, and here we're actually simulating the Navier-Stokes equation so that they wind up sampling the invariant measure of what these vorticity fields will look like at various times. And then you can trace this as just a conditional generation from given any time slice, what's the time slice? And we're not fulfilling the dynamics, so actually it's taking t omega t to omega t plus t, because that involves solving the Navier-Stokes equation. But instead, we're just trying to forecast. But the pitch is that you should draw a generative, construct a generative model that's already proximal to the target density. If I had this omega t, well, then only a small transport would be needed to turn it into any of these guys. Whereas if I did this with diffusion, I would actually have to take this guy, make it Gaussian noise, and then learn the math that takes that Gaussian noise conditional on this guy to this, right? So it's like making the transport problem harder. So the way you get this actually is related to this very specific process called the Fulmer process, which constructs a Schrodinger bridge between a point mass and the density associated.
Thanks. One more question? Yeah.
I can just pick up. So the kind of slide you have say that FD gives you like better performance compared to OD. Like and so in terms of other aspects, for example, would it be sampling faster than convergence? Like when you paint the picture of it like more than.
Yeah. So the ODE, this is a great point. If you really, so this is the trade-off you construct, right?
Right.
The ODE, you can, it is easier to solve, right? It's there's a whole suite of adaptive methods we have. The paths are easier to integrate. So you may be able to do this in fewer steps, right? But even if you did it perfectly, right, for your model, right, it still wouldn't be sufficient to bound the scale divergence. And if you're willing to pay, for example, the more steps you have to take to sample this SDE, right, then you actually do get control on the scale. And so we, for a while, were skeptical about if this is real, because, okay, it's a bound, how does it apply to the problem we do? But pretty much systematically, there's always an epsilon you can choose, right? This can be a time-dependent diffusion coefficient. How much noise are you adding to this sampling? That always seems to give better FIDs, better KLs, etc. And you can sort of imagine it as like, if you were wrong anywhere on this transport, like your B hat was not actually B, and there's no recovering, right? Like, yeah, for the ODE, from what the true trajectory was that you're trying to solve. But here, there's sort of a randomness that is allowing you to make mistakes, because if they're within the realm of sort of the scale of the noise, then it might be corrected on its own.
Thank you.
All right, yeah, we're gonna have 20 minutes break. We're gonna walk in the